Hello everyone, and welcome to another episode of Investigation. And in today's episode, I am going over one of the problems from the 4 sets of AMC problem that just went over days ago. And this problem is from AMC 10B number 22. So this is definitely a harder one. Before we get started, you can always comment down in the comment section below to let me know which one you're struggling with, and I will try my best to explain it to you. So let's get started. You can pause the video to read the problem, or you can just go to whatever websites like Art of the Problem Solving website and look at the problem, and you can think about it, and I will go over the solution just now. Okay, I will make the problem larger. Okay, I will just erase those then. Before I get started, I will show you some of the notations that I will use in this video, and I don't want you to get confused. So, the first one I am going to use is N choose R. That C denotes combinations, meaning the order does not matter. Like 1, 3, 2 is equal to 1, 2, 3. As long as these 3 elements are there, the order does not matter. And there's another one called NPR, meaning the order does matter, or permutation, which 1, 2, 3 and 1, 3, 2 are counted as different ones. And now, you may realize this as N choose R, as many of you are familiar with, but I'm going to use more formal expression of it. So, this is equal to N factorial over N minus R factorial, and that is basically N choose R, and this is equal to N factorial over N minus R factorial. So with this being done, let's get straight into the problem. It says Ang, Bag, and Jasmine each have 5 blocks, colored red, blue, yellow, white, and green. There are 5 empty boxes. Each of the people randomly and independently of the other 2 people places one of their blocks into each box. So we have Ang, we have Ben, we have Jasmine, who each have 5 blocks, or red, blue, yellow, white, green. That doesn't matter. We'll just denote it as 1, 2, 3, 4, 5, and each one denotes one color, and each one of them have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and finally 1, 2, 3, 4, 5. They're going to put it into 5 empty boxes with 3 blocks in each box. So let's draw that 3 empty boxes here. We want 5. That's my bad. I will do that. So these 5 boxes, because there are 15 blocks and each of them are putting one of each, so each inside each box there will be 3 blocks. And let's sketch our thinking a little bit. So the first we'll notice is that at least one of the box have 3 blocks all of the same color, meaning all ones in our case, our representation is just all of the same number. So if we draw that a little bit of Venn diagram here, that as at least 1. And we know that at least 2 is definitely inside it. But while counting at least 1, we have 5 of those. I can draw it here, but there are 5 of those. Because this box can have 3 of the same color, this box can have 3 of the same color, this box can have 3 of the same color, this box, and this box. So this representation of it does not really work. What we need is a 5-box Venn diagram, basically. So this is not going to be perfect because 3, 4 are really hard to draw already, and this Venn diagram may not be super clear. So that's the first, that's the second. We know that third must have intersect with each one of them. And the fourth, if you think that's right, no. We need a common place for this and this. So this representation is not right. How do we draw it as a 4-variable Venn diagram? As you might notice that each of these are really hard to draw because, like, if you draw something like this, it's not clear as well. So we'll revamp this a little bit. The first circle, let's just draw it here. Pretty easy. The second circle, we need to draw it like this. And each circle may not look like a circle because of the hardity that we would have here. And because the middle point will be pretty small, I will draw each circle pretty close to each other. And this should be something like this, and the 5th variable could be something like this. This looks super complicated, and I know, so I prepared an image for you. So here's the image that I prepared for you. This is a 5-variable Venn diagram, and we can see every 2 variable spaces are here, 3 variable, 4 variable, and 5 variable. So you can see that clearly. We want to calculate this area without the repeat of anything, right? So what we are going to do is, first of all, let me show you that each of this means 1 box that I represented up here. So in this box, this means A, B, C, D, E. And if I calculate one of the areas, if I calculate that at least 1 box is inside, at least 1 box has 3 colors, then I am going to over-calculate a lot of things. So let's see what I'm over-calculating here. So first of all, let's draw whatever A is. So I will do a check mark for each of the area that I counted. Check mark, 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 check mark. So these are all the areas that I counted for A. And now we're going to B. So this is check mark, 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 check marked. So these are all check marked. This is not in B. Check mark, check mark, check mark, check mark, check mark, check mark, check mark. So these are all the B's, and for C is check mark, check mark, check mark, check mark. This gets messy real quick, so this is just for visualization, and the conclusion definitely is not like how you would fare. against this. So of course I am going to, so C is this, so going to check mark those. And did I check mark this? I think, yeah. So for D, check mark, 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 check mark. I have no idea if some of these I missed or anything. So check mark, 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 not this. E. So what we have E here is this. So this, and yeah, all of these. So as you can see, this check marks may be a little bit messy, and I am going to make it better. And each time we calculate something as it labeled, we know that each of this is counted once, counted twice. So for this, it's just counted once, this area counted twice, this counted 3 times, twice, 4 times, 3 times, twice, 3 times, 4 times, 2, 3, 4, 5, 1, that's 2, that's 3, that's 2, that's 3, that's 1, that's 2, that's 3, that's 4, that's 3, that's 2, that's 1, that's 2, that's 3, that's 4, that's 2, that's 3, that's 1. So this makes it way clearer, and you can see that a lot of these are overcounted, and we don't want that. So we have to subtract out the things that we don't want. So the things that we don't want, let's say, let's subtract out everything that is 2 overlapped, and everything 2 of these overlapped, as so if we do this, at least 2 boxes have the 3 colors that we needed. So these 2. What we notice is that this part is actually overcounted, and we have to subtract 1 for each of the elements in this part. Essentially, we want every part to be 1 at the end. And this turns to be 2, this turns to be 3, this turns to be 4, this turns to be 3. This might be boring for many of you who knows the principle of exclusion and exclusion or pi, but this is a very, very good representation of how it works and why it works. All right. So we know that both of these are done. So that's 1, that's 2. So these are all revamped, and we essentially discover that some of these are not counted when they're supposed to be counted. So I'm not going to finish this because this is very tedious, and if you're interested, you can finish this through my I guess way. And the final thing is that we have to calculate everything with at least 1, subtract by at least 2, plus at least 3, minus at least 4, plus at least 5. So at least 5 is just all of them have the same color, which is just 1, 1, 2, 2, 2. Just making sure that you understand, like 2, 2, 2. This is 3rd box, 3, 2, 3. 4th box, 4, 4. 5th box, 5, 5. So these are all went over, and let's actually calculate it right now. So let's just calculate the base case that we have up here, and we don't have to worry about any of the probabilities yet, because we know that the total amount of ways we can calculate, because it's definite, it's not indefinite. So we know that at least one right here is 5 choose 1. 5 choose 1 times 5 pick 1. So 5 choose 1 is that it chooses whether it's A, whether it's B. So there we count A, count B, count C, count D, count E, meaning that's 5 of them. And 5 pick 1 is that we need to pick one of these. And finally, for this one, we have to times 4 factorial to the third, because this 5 pick 1, we're just picking one of the colors in one of the boxes. And the 4 factorial is the other 4 colors to the third, because each of them have to go, each of the 3 colors have to go to one of the boxes. We realize that we overcounted in this case. Let's just erase that. We realize that we overcounted the at least 2, at least 3, at least 4, at least 5 as shown in this Venn diagram. And at least 2 have 5 choose 2 times 5 pick 2. Pick 2 of the colors, throwing into the 2 of the boxes. So it's 5 pick 2 times 3 factorial, because there are only 3 colors left, to the third power. And we know that at least 3 is 5 choose 3 times 5 pick 3 times 2 factorial to the third, and 5 choose 4 times 5 pick 4 times 1 factorial to the 3, because there's only 1 color left. And we have to add 5 choose 5 times 5 pick 5 times 0 factorial to the third. And we realize that these are the only cases that we need to look at. And you might notice that I erased the arrows because some of these have negative coefficients, as I showed in the Venn diagram, or the principle of inclusion and exclusion. This is plus, minus, plus, minus, plus. And to save you guys' time, I'm just gonna calculate it for you. And this in total should get you to 120 times 2, 5, 5, 6. Why don't I multiply this out is because you can see that the total terms is 5 factorial to the third, as we showed here. Basically, at least 0, that is the total terms, at least 0, is basically 5 choose 0 times 5 pick 0 times the 5 factorial to the third, but these are just 1, so we don't need to take count. And this is the denominator that we need to take care of, and the denominator is 120 to the third power times 120 times 25 56 over 120 to the third power, if we cancel this out. And to save you guys' time, the final answer should be 71 over 400. And that is our final answer. Thank you for watching, and leave a comment down below if you want me to go over other questions in AMC 10, 12, A, or B this year. And good